which is directed to the fixed point, and this fixed point is said to be the center of the simple harmonic motion. And we know that this is proportional to the distance from the fixed point, and the force is minus mn square x, where m be the mass and n square be a proportionality constant and x denote the distance from the fixed point, and simultaneously act by a disturbing force. Okay, disturbing force, and for this is said to be forced oscillation, and disturbing force may be constant or may be periodic. Okay, and here we have to investigate the total motion or total effect of disturbing force on simple harmonic motion. Okay, and let the straight line, this is x, and let this is the fixed point, this is O. Okay, this is the center of SHL, and let P be any position of the particle at time t. Okay, and the distance from the fixed point O, this is x. We let this. Okay, and in this case, for the controlling force, if only controlling force appear, so the equation of motion or differential equation of simple harmonic motion, we write this motion as m into d2x by dt2. This is equal to minus m n square x. Okay, and in addition with this controlling force, if the disturbing force applied in this motion, and we know that disturbing force is always act opposite to the motion, let the disturbing force in the first case be constant, right, and its magnitude is F. And since disturbing force is always opposite to the motion, and this natural force always act for simple harmonic motion towards O. Okay, if we draw here, this is shown by arrow, this is natural force, this is m n square x. Okay, so the disturbing force must be in this direction. This is F, this is not only F, this is mf, because F is the disturbing force per unit mass, so mf is the total disturbing force. So in the equation of motion, we add this disturbing force here, mf. Okay, and by cancel out m from both sides and write this differential equation by differential notation, operator notation, this is d square plus n square into x, this is equal to f. Okay, so this differential equation have only two parts. X, this is the general solution, the first part is complementary function and the second part is particular integration. Okay, or particular integral. And what is CF? CF is obviously here CF, this is equal to A into cos nt plus epsilon. Okay, because two roots of auxiliary equation are imaginary, which are plus minus I. And particular integral, this is given by 1 by d square plus n square into f, and we write this is e to the power 0t. So particular integral is obviously f by 0 square plus n square, which is f by n square. So the general solution is a into cos nt plus epsilon plus f by n square. Okay, this is the general solution of this simple harmonic motion or this forced oscillation when disturbing force is constant. Okay, and we write this solution as x minus f by n square, and this is a cos nt plus epsilon. Okay, if we put the left hand side, this is equal to y, so we get y, this is equal to a cos nt plus epsilon. And if there is no disturbing force, then the solution of this differential equation in absence of capital F, we know that this is x equal to, x equal to a cos nt plus epsilon. Okay, this is the natural simple harmonic motion, or this is the motion under control force. Okay, and here a be the amplitude and 2 pi by n be the periodic time. So these two are unchanged by applying disturbing force, which is constant. Okay, and only one change here. Here x change to y, and here if we put x equal to 0, then we get this is the position of fixed point, or this is the center of the simple harmonic motion. So to find the center of the simple harmonic motion under disturbing force, we get y this is equal to 0. So we get x this is equal to f by n square. Okay, so we say that if we use, or there be a disturbing force which is constant in magnitude together with the controlling force of a simple harmonic motion, then the periodic time and amplitude are same as earlier, and only one change, which is the center of the oscillation is shifted to O, shifted from O to O dash. Okay, O to O dash, where O dash, this is given by f by n square. This is the only effect of disturbing force, which is constant. Okay, now we discuss the effect of disturbing force when this disturbing force is periodic. Let it be f cos p. Okay, and that is the period of the disturbing force is 2 pi by p here, and so mf changes to mf cos pt. Okay, and then the equation of motion changes mf to mf cos pt, and this equation can be written again as this is only cos pt. Okay, and it has also two parts. The first part is cf and second part is particular integral. Okay, and first part is same as the previous. We write the complementary function directly. This is a cos nt plus epsilon. Here also this is the amplitude, and this is 2 pi by n. This is periodic time. Okay, now to find the particular integral, this is d square plus n square f cos p, and here we get two cases. Okay, in the first case, case 1, this is the case when n not equal to p. Okay, and when n not equal to p, then we get particular integral. This is given by 1 by d square plus n square into f cos pt. So this is given by 1 by minus p square plus n square f cos pt, because we know that if we put minus p square in place of d square, and if this term is not 0, then this is the particular integral. Okay, we know it by the process of finding particular integration of differential equation. So this is given by f by n square minus p square cos pt, and in this case general solution is x equal to cf. This is a cos nt plus epsilon plus this is f by n square minus p square cos p. Okay, and clearly this is a periodic motion, and this is also a periodic motion. The period of this motion is 2 pi by n, and period of this oscillation is 2 pi by p. Okay, and amplitude is constant, which is given by A, and in this case amplitude is also constant, which is given by F by n square minus p square. Okay, and now if n is nearly equal to p, then we get n square minus p square. This is tends to 0. Okay, so this amplitude becomes very large. In this case, the first oscillation, this is also known as tree oscillation. Okay, and for the second oscillation, this is known as forced oscillation. Okay, and since in this case, when n is nearly equal to p, then this amplitude is very large than that of A. Okay, and this oscillation, that is the forced oscillation, are of our primary importance. Okay, and ultimately this motion becomes the forced oscillation with the period 2 pi by p, and in this case this motion have no importance because this amplitude is very large than that of A. Okay, and this is the case when n not equal to p, and when n is nearly equal to p, and in this case, since the amplitude of the periodic disturbing force, that is 8 by n square minus p square, is very large, for this reason this motion is said to be the forced oscillation. Okay, and for which the topic name is forced oscillation. Okay, now we go to the last case, which is given by n equal to p, and this is the case number 2. And where n equal to p, then we know that the particular integral is different from the previous, and in this case 1 by d square plus n square into f cos pt, and which is given by, we use the formula directly, this is t by 2 into integration cos pt dt. Okay, so f t by 2p into sin pt. And in this case, the general solution of this motion of the differential equation is given by x equal to, this is same, a cos nt plus epsilon, and for the particular integration, this is ft by 2p into sin pt. Here the amplitude is a and periodic time is 2 pi by n. Okay, and for the second motion, that is for the periodic disturbing force, here amplitude is ft by 2p, and the period is 2 pi by p also, because this term sin pt can be written as cos of pi by 2 minus pt, or cos of pt minus pi by 2, we can write this. So the periodic time is same. So two periodic time are same because n equal to p. But it is clear that with time, as t tends to infinity, then the amplitude of the disturbing periodic force f t by 2p, this is tends to infinity also. We give priority to the disturbing periodic force because this amplitude is very large than A. This is constant amplitude, and in this case, when n equal to p, we occur the situation where the amplitude ft by 2p tends to infinity, and this is said to be resonance. In simple harmonic motion. Okay, this is very important term of simple harmonic motion, which is said to be resonance in simple harmonic motion. And this is the total discussion of forced oscillation of simple harmonic motion. Okay, thank you for watching.